Welcome to this explainer. Today, we're looking at something I like to call the accordion effect. We all live our lives completely surrounded by devices that seem, well, infinitely capable of capturing our world in high-definition photos, endless video streams, and crystal-clear audio. But have you ever actually stopped to think about the digital weight of all that media? Our digital footprint is constantly expanding. So in this explainer, we're going to look at exactly how we manage it, measure it, and somehow miraculously squeeze it all down to fit right in our pockets.
Now, it might sound like a joke, but do you actually know what a nibble is? Or why a seemingly simple photograph or a short little voice memo can suddenly take up so much space that your phone starts begging you to free up storage? We interact with gigabytes and terabytes every single day, yet the abstract math behind these digital files clogging up our devices, it often remains a total mystery. Well, today we're going to demystify the whole shebang. We'll reveal the answers behind the invisible architecture of your digital world. And yes, for sure, I will tell you exactly what a nibble is in just a second.
To get there, here's our game plan. 1. Measuring digital storage. 2. Calculating file sizes. 3. Why we compress data. And 4. Lossy versus lossless methods. It's a journey from the absolute smallest units of data up to massive theoretical limits, and then showing how we squeeze it all back down.
Section 1. Measuring digital storage, the building blocks of data. Okay, let's dive into this. To truly understand our digital world, we have to start at the foundational building blocks and see how they scale from the micro to the macro.
It all starts with a single bit. That's the fundamental atom of digital storage. From there, we step up to that funny word I mentioned earlier, a nibble, which is exactly half a byte, or 4 bits. But things really get practical when we hit the byte. A byte is made up of exactly 8 bits. And from the byte, we launch into the stratosphere. We scale up to the kibibyte, the megabyte, the gigabyte, and the tebabyte. But it doesn't stop there. As our data needs absolutely explode, we push into the truly massive realms of the petabyte, and incredibly, the exabyte. I mean, think about the sheer scale of that progression for a second. We are taking that tiny single 8-bit byte and multiplying it upwards until we reach exabytes. We're talking quantities of data so vast, they can represent the digital output of entire global networks. It is a completely staggering hierarchy.
Now, the crucial point here is this number, 1024. This is the surprise trap that catches so many people out. When we scale up from one denomination in that massive hierarchy to the next, we do not multiply by 1,000. It's a super common misconception, but you literally must erase the number 1,000 from your mind when calculating these storage sizes. The amount of the previous denomination present in the next size up is always based on 1024, because computer storage is built entirely on binary math, or powers of 2. So, for example, there are exactly 1024 megabytes in a gigabyte. Remember this number. Using 1024 instead of 1,000 is absolutely the golden rule of digital storage mathematics.
Section 2. Calculating file sizes, the mathematics of size. Now that we know our building blocks, let's put on our analytical hats and figure out exactly how heavy these uncompressed files actually are.
If you want to know the size of an image, you really just need 2 raw ingredients. You need the image resolution, which is simply how many pixels there are, and the color depth. Once you have those, you just run your calculation. But remember our golden rule? You always divide by 1024 to scale your units properly, making absolutely sure your final answer matches the specific unit you're looking for, like megabytes.
Now, what's really interesting here is that we apply a very similar procedure to audio files, just with slightly different ingredients. Instead of pixels, you need the sound sample rate, the sound resolution, and the actual length of the track itself, like a 10-second audio clip or a 3-minute song. Combine those 3 variables, execute the calculation, again relying strictly on that 1024 rule to scale your units, and bam, you get the true uncompressed weight of that audio file.
Section 3. Why we compress data, the squeeze. If you actually ran those calculations for every high-resolution photo and audio track sitting on your phone right now, you'd realize the weight of uncompressed data is astronomical. And this brings us to the hero of our story, data compression. The entire purpose, the fundamental need for data compression, is simply to reduce the size of the file. But the impact of that reduction? That is what makes our modern digital lives possible. Just think about the everyday frustrations you experience. Staring at a buffering video, getting that dreaded storage full notification right when you want to take a picture, or agonizing over a painfully slow download. Compression exists to solve these exact problems. By reducing the file size, the impacts are immediate and powerful.
You require way less bandwidth to move the data across networks. You require significantly less physical storage space on your hard drives. And you get much shorter transmission times when sending files to a friend or streaming from the cloud. Compression really is the invisible engine of efficiency.
Section 4. Lossy versus lossless methods. Trimming the fat. Let's move to and see how this builds. We know why we need to compress data to survive in the digital age, but how exactly do we collapse this accordion without completely ruining the file? Well, this brings us to the two main strategies we use.
This perfectly illustrates the ultimate trade-off in data storage. On the one hand, we have lossless compression. Just as the name implies, this method reduces the file size without any permanent loss of data. When the file is opened again, it's a perfect identical copy of the original. A prime example of this is run-length encoding, or RLE, which saves space by simply grouping identical, repeating pieces of data together instead of recording each one individually. It's highly efficient, but it definitely has its limits. On the other hand, we have lossy compression. This is a much more aggressive approach. Lossy compression shrinks the file size by permanently removing data. It literally throws information away that it deems unnecessary. How? By actively reducing those very ingredients we used in our calculations earlier. It might reduce the image resolution or dial back the color depth. For a sound file, it might reduce the sample rate or the sound resolution. Once that data is gone in a lossy format, you can never get it back. It's a permanent sacrifice in the name of saving space.
Which leaves us with this final thought. We rely on the 1024 rule to measure our growing digital footprint, and we rely on compression to keep it manageable. But knowing that our most effective tool, lossy compression, works by literally throwing data away, how much of your digital world are you willing to permanently delete just to make it fit? It's a really fascinating trade-off we make every single time we snap a photo or record a sound. Thank you so much for joining me for this explainer, and I really hope this gives you a whole new perspective the next time you check your device storage.